Welcome. Hi, Richard. We can't hear you yet.
Can now.
I can start introduction if you want to get started in a couple of minutes.
Yeah, let me just fire up my keynote. Make sure. Can I share screen?
Yes, you can.
How's that? You guys can see it?
Yeah.
You can see that.
All right. Welcome back, everyone. We have our first invited speaker, Richard. He's a professor at the University of Auckland, and we're really happy that we have him to tell us more about what he does and so covers everything really. So because we've had a long break already in the morning, and we have some really good talks, so I think we'll prepare your questions. So this is a chance for you to ask questions. So some of us have been quite quiet, so I really encourage everyone to think of 1 or 2 questions to ask Richard. We have plenty of time. All right. I'll let Richard to get started. Thank you. And is that Frank? Do you want to record it, or whoever can record it, please? Thank you.
Someone's recording it by the look of things. Are we set to go? Firstly, just wanted to congratulate everybody. Hang on a minute. What's going on in the chat here? Where's my mouse gone to, for that matter? Hang on. Do I need to see this? Okay, cool. Recording is okay. Whoops. Hang on a minute. Let me start this again. Yeah, trouble with my mouse. So yeah, I wanted to congratulate the organizing committee for pulling this together, and it's good to see just the development of as part of a stronger community in gravitational physics and Australia and New Zealand, and obviously particularly excited to be contributing this for here in New Zealand, where we look with some envy across the Tasman to our larger and better organized cousins. So my focus today is on understanding the very early universe, and in particular making sense of the sort of what's sometimes called the primordial dark age of the universe. And that is both in the sense of that we don't really understand what's going on, but also dark in the sense that we know that the early universe is hot, is full of radiation. And we know that because we look at the success of Big Bang nuclear synthesis in terms of explaining the number of small atoms, or the kinds of small atoms that we see in the universe, deuterium, lithium, helium, but also that that it lays the groundwork for the microwave background. But the early universe wasn't necessarily always hot, and at very high energies, we have no idea what the rules of physics are, and we have very little idea what the universe would have been up to in that time. But it also necessarily, that phase lays the groundwork for the way that the universe subsequently evolves, and also potentially gives us insight into physics that applies at energies that are far beyond anything that we could dream of reaching at the LHC or any of its conceivable successes. So I'm hoping that I've got a bunch of things that I can say. So obviously happy to stop and take questions at any point. But just also want to thank I've got an excellent group of collaborators and students, both locally and internationally. Frank is one of the organizers, so Frank in particular, but a really good group of people that we're working together with on this. So I just wanted to start with something really simple, and so even if you're not like a dedicated cosmologist, something you can take away from this, and that is the question of how small can the universe be, at least in terms of us being able to describe it using the tools of general relativity. And so quantum mechanics tells us that a particle of mass m has an associated wavelength, h bar over m times the speed of light. And so now we can ask, how big would a black hole be before it is smaller than its own Compton wavelength? And so we just set that length to the, to the Schwarzschild radius of a black hole. And we get a relationship, one of which is, m upstairs, one of which has m downstairs. And so it gives us that the mass of this tiniest meaningful black hole is the square root of Planck's constant times the speed of light divided by Newton's constant. And that's the number that we call the Planck mass. And so we can very quickly turn that into an energy, to a temperature, to a length scale, using the various numbers that we have to play around with. But as a kind of physical quantity, it's about 2 times 10 to the minus 8 kilograms. It's apparently about, according to Wikipedia, I'm not an amoeba specialist, but apparently that's about 1/10 of an amoeba, a deci-amoeba. So something that's tiny, but something that you would be able to see easily through a microscope. So if we define the Planck length, the radius of a Planck mass black hole, and we've dropped a factor of 2, and we say, well, that's the size of the smallest black hole that we can have. But it's also, if we think about it, if we want to probe a length scale that is smaller than that, we're going to have to use a probe that is more massive than that. So it defines the kind of the smallest meaningful scale that we can expect to have space-time at. So it's also, the minimal length or the minimal size that the universe can take. And so it's about 10 to the minus 35 meters. So the universe, even though singularity, our space-time can't have been sensibly smaller than about 10 to the minus 35 meters across. So the Planck time is just the light crossing times the black hole, so 10 to the minus 44 seconds. We can turn that into joules times the speed of light squared. That gives us about a ton of TNT, it turns out, is about the same energy as that. And so, we have the uncertainty principle is telling us that, we can't get, the total amount of energy smaller than the total of delta E, delta T. And so all of these things come together to tell us this is the kind of smallest scale of space-time. So here's a, artist illustration of, quantum foam in the early universe, some observers there. Obviously not exact impression, but always get the sense of what it would be like to try and make sense of the very early universe. So we're going to turn this around, and we can also ask, how big is the universe as a whole? And so the visible universe is somewhat paradoxically about 40 billion light years across. And so that, for those of you that are paying attention, that's about 3 times the age of the universe in light years. And so the reason for that, as we ask our cosmology students, is that, the universe is expanding. So light that is set off from a distant galaxy has only had to travel a little bit less than 13.8 billion years. But on the other hand, that galaxy has moved away from us since the light was emitted. And so when we sit down and do the math, it's roughly a factor of 3, would be exactly a factor of 3 if the universe was perfectly matter-dominated since inception. It's messed up a little bit by the discovery of dark energy, but roughly the third age of the universe times a factor of 3 is the physical size of the visible universe. So the Planck scale is 1.6 times 10 to the minus 35 meters, and so 40 billion light years is about 10 to the 61 times larger than that. So what that tells us is it tells us that if the Big Bang is some sort of quantum gravity thing, it tells us that the total growth of the universe that we have to worry about observationally is about 60 factors of 10 since the Big Bang. Not an infinite amount, but also not a small amount. The interesting trick of this is we also know how hot the sky is, and this obviously dates back to the discovery of the microwave background, which happened, serendipitously in the 1960s when people were in fact looking to build more sensitive communication satellites, but they found that their antenna kept on picking up what was apparently a 2.7 Kelvin black body. And when they went looking for the origin of that, they realized that they'd literally stumbled over the origins of the universe. So we know how hot the sky is. We've mapped it now in some detail. But we know that that the universe was hot as has some temperature today. We also know that if we take a gas of photons in the expanding universe, then as the universe expands, two things are going to happen to those photons. Firstly, just as the volume of the universe gets bigger, the number density of photons in a given cubic meter is going to go down. But also each of those photons is going to be stretched by the expansion of the universe. And as they're stretched, their wavelength is going to go down. And so the total amount of energy that exists in radiation in a given volume scales like the size of the universe to the fourth power, or 1 over the size of the universe to the fourth power. We can calculate how far we have to go back in time before the density of the universe, or the component of the universe in radiation, is denser than the component of the universe that is represented by matter. Because the matter, the density of that scales like 1 over a cubed. So if we make the universe 1,000 times smaller than it is today, the relative fraction of matter and energy in the universe, or matter and radiation in the universe, is going to change by a factor of 1,000. So for most of the existence of the universe, for all about the last 4 factors of 10, the last 10,000, factor of 10,000 in growth, for most of the universe, of the growth of the universe, it would appear that the universe was dominated by radiation. In other words, that most of the stuff in the universe was the radiation that we see in the microwave background, scaled back appropriately in density. For 56 orders of magnitude of the universe's growth, we would assume that it was radiation dominated. So that's interesting, because that tells us when the universe was 1 billion times smaller than it is today, the temperature, if we switch from kelvins to electron volts, would have been about 0.6 MeV, minutes after the Big Bang. So at that point, nuclear reactions can happen. We go back 1 trillion times smaller than it is today, much less than a second after the Big Bang, where we're getting the time scale from solving the Friedmann equations. The temperature is up in the GeV area. We can imagine PET producing electrons and positrons, for instance. A quadrillion times smaller, we're at TeV scales. We're a trillionth of a second after the Big Bang, and we're looking at typical interactions in the universe happening at energies that we would need the LHC to replicate on the Earth. So our 2.725 Kelvin blackbody peaks at about 160 gigahertz. So we know that E is equal to h nu, so we know how much energy each of those photons has. And so a typical photon in the microwave background has about 10 to the minus 22 joules worth of energy, or about 0.0006 electron volts. So as I said, the photons redshift as the universe grows, the universe cools as it expands. So what we could ask is, how far back in the history of the universe do we have to go before the energy of each of the photons in the universe would hit the Planck scale? And so the Planck energy is about 10 to the 9 joules, so, the E equals mc squared mass of that Planck mass black hole. That corresponds to an energy of about 10 to the 19 GeV to get that ratio to come right. And so when we look at that and we see what's happened, we need to get about 10 to the 30 worth of growth of the universe to get each of the photons in the microwave background up to Planck scale energy. So that's the 10 to the minus 22, and the 22 and the 9, we add them together and we get 10 to the 31. We call it 10 to the 30 because we're friends. So that gets us also to the Planck density, where the density is necessarily of the radiation is necessarily the fourth power of the temperature. So we have about 10 to the 60 worth of growth that we've got to account for. But it turns out by the time we get to 10 to the 30 worth of growth, if we just take the energy that the contents of the universe that we see today, apply the laws of physics, we understand them, and extrapolate backwards, we hit the Planck temperature and the Planck density when the universe is only about 10 to the 30 times smaller than it is today. And so what that tells us is, it tells us that the total expansion history of the universe, if we want to go all the way back to the Planck size, has got to be something other than something that's strictly radiation dominated. This is going to get us into trouble. So this is one, it turns out, of many ways of quantifying problems that are associated with what we might call the standard Big Bang. And so there are other ways of looking at it. Why is the universe so flat today? Why is the spatial curvature of the universe so close to the magic number that it needs to have in order to be balanced between expansion and contraction? You know, why are there no magnetic monopoles in the universe if they can be made in the very early universe? There's a whole bunch of things that we would like to be able to explain on the, you know, that essentially the initial conditions of the universe, all of which turn out to be the fact that somehow the early state of the universe has to be very, very fine-tuned. The question of the radiation dominated, well, this radiation question is one that I haven't seen sort of expressed in a lot of detail previously, but this is just one way of looking at the problem. So the solution to this problem is what is typically known as inflation. And this is an idea that has been around since the early 1980s, most associated with the name of Alan Guth. But someone, you know, there's a variety of people who are having similar ideas at the same time. Alexei Starobinsky, yeah, to go back and dig up the names, Katsuhiko Sato in Tokyo. There's about 4 or 5 people, Rocky Kolb, Stephen Wolfram, who can claim to have invented various aspects of this idea. And so the solution to this idea is to say that the universe grew by about a factor of 10 to the 30. So the other factor of 10 to the 30 that we need to add to the radiation content, while the density changes relatively slowly. And so it can't be a thermal state during that phase, because we know that as the universe expands, thermal material, you know, a thermalized material is going to scale, you know, it's going to be diluted by the expansion. It has to be experimentally inaccessible. It's at very high energies. Nothing we can see in the standard model of particle physics has the right properties to do this. So how are we going to make this happen? And the way we make this happen is by what we call cosmological inflation. In other words, something that's near exponential expansion of the universe. So time during which the universe is growing, you know, each time it grows, you know, each passing constant unit of time, the universe effectively doubles in size. The way we make this happen is by filling the universe with material where the pressure is close to kind of as negative as it is allowed to be. And negative pressure is simply coming from material that when you stretch it, you are adding energy to the material. In other words, if I take a spring and stretch it, the spring is going to be somewhat heavier after I've stretched it than beforehand, because I've had to put energy in to do that. You know, I've separated out the bonds between the atoms. If I was to put that spring on, you know, at least as a thought experiment, on a very accurate scale, I would see it come out heavier than it had been to start with. So negative pressure, that's opposite of an expanding gas. If I want to extract work from that material, I would allow it to contract. And so, you know, negative pressure sounds mysterious, but it's simply something that, you know, in order to get it to do work on the universe, it would contract rather than expand. And so with the speed of light equal to 1, we can measure pressure and density in the same units. And it turns out, as long as you don't want to violate things to do with causality and sort of the various null energy hypotheses that go into general relativity, it turns out we can't have the pressure less than the density, P less than minus rho. But if we set P exactly equal to minus rho, it tells us that the amount of energy that we're storing in the fabric of, you know, the kind of contents of the universe as it expands, mean that as it expands, its density is going to remain constant. So that tells us what to go and look for. We also know that inflation, that this primordial inflationary phase has to come to an end. If it doesn't come to an end, at least locally, it means that the universe would still be inflating, would still be dominated by this stuff, and that's not the universe when we look out the window today. So the universe would be cold. You know, any particle states in this early universe would be diluted away by this near exponential expansion. So it's if you took a particle detector and you put it in the early universe, you would see that, you know, while the early universe was very dense, there were essentially no particles in the universe. So when this inflationary phase comes to an end, you need some process that takes the energy out of the inflation, whatever material has supplied this negative pressure, and converts that eventually into radiation, into standard model particles, either photons and neutrinos, which are almost massless, but also at very high temperatures, your regular other, electrons, muons, quarks will be able to move freely and will be moving at relativistic velocities. So will be effectively behaving like massless particles. You have to explain how the perturbations we see in the microwave background form, these are thought to be laid down during the inflationary phase. We also have to account for the physics of neutrinos, which because these are almost massless but not quite massless, they contribute in various interesting ways. So modern cosmology is built on dynamical spacetime in 1915. We have our first basic cosmological solutions that Friedman and Lemaitre both broke down solutions that we now recognize as the expanding universe in the 1920s, a little bit more polished, provided by Robertson and Walker in the 1930s. And inflation in the 1980s grafted a kind of new root onto this existing tree, onto this cosmological model that had first been described in the 1920s. So the physics of this is that the way that we go about making negative pressure is we take something that has a scalar degree of freedom, so something like the Higgs field, but not the Higgs field because it doesn't have the right detailed properties to do this. And this field, we don't know what it is, but we call it the inflaton because that kind of makes it sound a little bit more official than just calling it something you made up. It can be a fundamental field like the Higgs, something that's in the Lagrangian of some particle theory, or it can be something that emerges as a degree of freedom from some deeper theory. So string theory, for instance, has a lot of degrees of freedom that behave like scalar particles, but are somehow associated with, fields that live in extra dimensions or the size of compact spaces. And you have to have just the right kind of properties of the scalar field, in particular its interactions with itself, to provide the negative pressure that you need to do this. And as I said already, the particle content as the universe, once inflation begins, whatever particles are in the universe before it starts will be exponentially diluted. So I'm not going to get into the details of the kind of cosmological problems that inflation solves, but we're left at the moment with this hypothesis that we can solve the problem of why is it that if we make the universe 10 to the 30 times smaller, it looks like the microwave background would be at kind of Planckian energies. But if we need to make it 10 to the 60 times smaller in order to get the volume of space that we live in today, back to the point where we could imagine it being created by some quantum gravitational process. And what inflation does is it takes pretty much whatever early universe you give it, and it drives that universe very much in the direction of it being spatially flat. In other words, balanced apparently between expansion and contraction. Almost exactly smooth. So whatever lumpiness you have in the universe before inflation begins, you create a universe through some process. We know that babies are kind of messy. So inflation has the job of kind of taking whatever baby universe you produce and making it almost but not perfectly smooth on large scales. It lays down the perturbation. It's not exactly smooth. It lays down the primordial perturbations, which have to be there, before the CMB is formed. So they can't be formed, somehow by nonlinear processes. In the late universe, we see them in the polarization patterns of CMB. We see large-scale correlations in the sky that must have been sort of laid down in ways that are very hard to imagine happening causally. And we see that those perturbations are Gaussian, and we see that they're adiabatic and sort of another kind of technical requirement. What we don't understand, even though we've got lots of models of inflation and we can test them in some detail by looking at how they, what they predict, for the, whether we expect, more big galaxy clusters and small galaxy clusters, inflationary models make a prediction about that. So we can test that against observations. What we don't know in general is how inflation comes to an end and what process then produces a universe that is thermalized on large scales. It's also frequently said that inflation produces a primordial background of gravitational waves. In other words, like the CMB, like a bath of gravitational waves that fills the universe, rather than the kind of point sources that we see with LIGO and Virgo. It's true that it does that. It's also true that the amplitude of those gravitational waves varies a lot between models. And it's very easy to imagine an inflationary scenario where the gravitational wave amplitude is effectively small enough so that they're effectively undetectable. So where this gets us is a picture that says that on a kind of, logarithmic timescale, where we're measuring the expansion of the universe in terms of factors of 10. Remember, we need about 60 factors of 10 to get us from a patch of sky, a patch of space that is kind of, plausibly quantum gravitational, to be big enough to fill the, to account for the entire volume of space that we see today. So this picture would tell us that about 30 of those factors of 10 happen during this inflationary phase. And in canonical pictures of inflation, that whole period of growth happens in about 10 to the minus 32 seconds when you put in appropriate numbers. But it's driven by unknown or new physics. That dumps potentially the universe out of inflation into a situation where the energy density is about 10 to the 15 GeV to the fourth. In other words, that's about 10 to the 12 TeV. So remember, the LHC has interactions that top out at about, at a few TeV. So 1 trillion times higher energy than the LHC. So if the universe thermalizes at that scale, it's going to need to grow 1 trillion times larger before typical interactions have reached a point where we might be able to think about testing them in a terrestrial accelerator. And then it's going to grow 1 trillion times larger again before we get to the point where, the universe is plausibly, the universe as we see it today. So what that tells us is there's about 15 decades of growth at temperatures above those energies probed at the LHC. And another 15 decades of growth, 15 factors of 10 between energies hitting LHC scales and reaching the kinds of energies that we see in microwave background photons today. So the weird thing is that about 45 of those 60 factors of 10 that we need to account for the total expansion of the universe happen at energy scales and involving kind of rules of physics that we do not understand, that we cannot probe experimentally, where we have hypotheses, but we don't have, detailed tests of what's going on. But that whole 45 factors of expansion, also in sort of conventional cosmology, happens in about 10 to the minus 12 seconds. So 75% of the growth of the universe in logarithmic terms is happening in 1 trillionth of a second, and everything else that happens in the universe, the last 15 factors of 10 takes about 13.8 times 10 to the 9 years, about 13 billion years. The first stars light up in about the last decade of expansion. There's debate at whether the JWST is showing us galaxies and a redshift of 15. But remember, if we're thinking of factors of 10, 1 decade gets us a factor of 10. 2 decades of expansion would get us a factor of 100, and there definitely weren't stars at a redshift of 100. And so the universe only becomes transparent, in fact, during that last 3 decades of expansion. The CMB, we can calculate with some accuracy, decouples from the rest of the universe at about when the universe is about 1,000 times smaller than it is today. So everything that we think of as the sort of interesting parts of the universe, or the interesting pieces of the universe that we can see, they're basically happening in one last skinny little sector of that that sub TeV region that I've written down there. So this when I talk about the primordial dark age, what I'm talking about is the period after the end of inflation and before physics becomes well behaved, or at least described by experiments that we can do at the LHC. The universe grows by about a factor of 10 to the 15 during this phase, if we assume that inflation is the thing that happened, which means that that's about the same amount of growth that happens afterwards. So even though it happens very quickly, the universe gets a lot bigger during that stage. And because things in it are happening very quickly, there is a lot of time for complex processes to happen at very high energies in the universe during this phase. So that, as I said, it's about a quarter of the growth of the universe in logarithmic terms, lasts about 10 to the minus 12 seconds. Energies beyond the reach of the LHC, said this already. Okay, So during that phase, we think that dark matter has to form somehow, because we know that there's dark matter in the universe, as it sort of rolls into its present form. We think it's somehow associated with high energy physics, because we can't make dark matter in the lab. So that's telling us that most likely the dark matter content of the universe is laid down during that phase. Otherwise, you've somehow got to sneak it into the phase where we think we understand the laws of physics. Baryogenesis has to happen. In other words, we want to produce the baryon content of the universe. We need to explain, the matter-antimatter asymmetry. There's an old theorem by Sakharov that says that has to happen at a time when the universe is out of equilibrium. So again, that's telling you that things can't be kind of smooth and sort of balanced all the way through that phase. And we also need to account for thermalization. We've got to somehow take the energy that's locked up inside of the inflaton field, and we've got to turn that into standard model particles that will eventually lead to a universe that has protons and neutrons in it a couple of minutes after the Big Bang. So these are questions that we can ask. How did inflation happen? Did inflation happen? Can we really prove, this is ultimately a hypothesis. Can we, prove it beyond a shadow of a doubt? And if we think that inflation happened, how can we, even if we can't prove inflation as a whole, we can certainly test competing models of inflation. And they're all good questions, and they're all things that I've worked on at various times in my career. What I want to talk about is this post-inflationary phase, the so-called primordial dark age. And so we know that the universe has to thermalize because we want microwave background nucleosynthesis, primordial and neutrino background. And we've also got to somehow ensure that, that we get baryogenesis, matter-antimatter symmetry breaking, generation of dark matter. So that all has to happen during that 10 to the minus 12 seconds. So I'm not going to get deeply into the kind of detailed physics of inflation, but we can write down for a given inflationary model, we can write down a potential that describes the way that the inflaton varies as a function of time. And we know that the inflationary phase corresponds to a region where if you change the value of the fundamental field, the value of the potential doesn't change by very much. And so this one is from a particular paper. There are literally hundreds of proposals for how inflation works. I pulled this one at random because it's a nice picture. It's not significant beyond that. What will happen is the inflationary field will kind of roll down this potential and the field wants to find regions where the potential is lower. And then when it gets into the bottom of the potential, it will oscillate, inflation will end, and when the field starts moving rapidly, it will oscillate around the minimum at the bottom of the potential. So we can imagine processes that are very quick and efficient at producing thermalization at the end of inflation, but it's not guaranteed, and it doesn't need to be quick because remember we've got that 15 orders of magnitude in growth that's allowed to happen before we think that the universe really should be thermalized, maybe even longer if we're going to let ourselves push into standard model energies a little bit. And so there's about 3 different ways that inflation can come to an end. The first way is that the inflaton, as it oscillates, it's a time-varying forcing term. And if you've got a small perturbation in the inflaton field that's coupled to it, that oscillation and the amplitude of that or the wavelength of that perturbation can be such that you exponentially produce some momentum modes of the field that it's coupled to, which means that very quickly the inflaton field fragments. And the universe on small scales becomes very inhomogeneous, even though it remains homogeneous on large scale. You can couple another field to the inflaton, and you can produce it through the same resonance. You can produce particles that have, when you account for the spin of the particles, it turns out Pauli exclusion principle actually makes this more efficient for fermions than it does for bosons. But we don't know the particle physics of inflation, so we don't know the couplings of inflation of the inflaton field to other fields. The last case is that there's no resonant production of anything, that the inflaton field just kind of continues to quietly slosh around the bottom of its potential. I might skip, this is an example of resonance. So it's going to show. So this is the inflaton field. This is the spatial cross-section. And it's sloshing around the bottom of its field. The one on the right is another field that it's coupled to, and we see that firstly we get a inhomogeneity in the coupled field, and then that turns around and drives inhomogeneous behavior in the field, in the inflaton field itself. And so you wind up with a universe that's very, very lumpy on small scales. So this happens very quickly. It can produce, in particular, you're driving the contents of the universe inhomogeneously at very large, at high intensities. This process produces gravitational waves, potentially that would have gigahertz frequencies in the present universe, a significant amplitude. No one's got a clue as to how to go and find them, but it's at the very least an interesting problem, and one that may provide a direct way of testing the behavior of the early universe, something that I've worked on a fair bit. But the next question, and I can stop and next issue on, let me stop and ask if there are any questions here. It's a little bit, I'm not seeing my audience, but happy to stop and take questions about where we've gone, because the last little bit that I want to talk about is the sort of the specific things that we've been working on here for the last couple of years. But any questions about this, or any questions so far?
Doesn't seem like him yet.
How's the chat doing here? Happy to keep. I mean, just wanted to stop and take a breath at this point. I can't see people's faces. It's also perfectly clear. That's remarkably kind of you to say that. I'll take that encouragement and continue then. Unless anyone wants to argue with that.
I wish to ask a question.
Sure, what was that?
Oh, I was just wondering, because earlier we had this minimum Planck length from the uncertainty principle. Would we have minimum momentum as well?
I think it's more maximum momentum. Minimum momentum is easy because that just means you're
I mean, a minimum momentum uncertainty.
Hang on a minute. Well, so the momentum uncertainty is always the trade-off between the time and the place. But what this means is that if you try to probe space-time on lengths that are smaller than the Planck length, then you have to use a probe that in some sense won't, to be small enough, it wouldn't fit in, it's a quantum probe, but it wouldn't fit inside of its own event horizon. So at that point, space-time becomes kind of weirdly grainy. You can't, if you try and, build a microscope that has, Planck length photons, they wrap themselves in little event horizons, and you try to look on scales smaller than that, the probe that you've produced isn't going to fit inside of its own event horizon. So it's a slightly sketchy argument. But it means that you can't sensibly think about, even though we think about, or the universe is grown by an infinite amount, because the initial, if you look at classical solutions of the Einstein equations, they tell you that, like when t is equal to 0, the universe is infinitely small. And so it looks like we've had an infinite amount of expansion, but we really haven't. We've only, at least in the context of a cosmology that we can describe with general relativity and quantum mechanics. It's a very broad set of ideas. We know that the universe has a finite size, because there's a limit to how far, photons can travel in the age of the universe. But it means that you can cut it off at large scales, which is where that 10 to the 60 comes from. So I guess there's an upper limit to the momentum of any given particle, but there's also, like once you start to worry about, if you say, well, I want my have 0 momentum, then that would mean that you were looking on a very long time scale, and cosmology doesn't necessarily give you the luxury of being able to do that. You want to, if you wait too long, if delta t is too long, then the universe will have changed on you. So that in some sense puts a lower limit on that delta t, which I guess also puts a lower limit on the momentum of any given state. I mean, I'm not 100% sure about this. I'm just pulling it out of my ear, but I think if you pursued some form of that line of reasoning, we know, for instance, that if you take an expanding universe, an exponentially expanding universe, it's what we call the Sitter space. And that has some temperature that's associated with it. And so, that's telling you that you're, like there's some time, and it's telling you that you're creating quanta off the horizon, but that's taking me in a direction that I don't want to go at this point. But I think you would find that, there's a minimum amount of momentum that you can have as a quantum state in a Sitter space. At least I think that's true. I may have just said something On the inflation plots, what are the axes? So the potential, so the inflaton field is just it's a scalar field which has some number wherever you are in space. And so if you set the value of that scalar field, there's some energy density that's associated with potential. So we assume, or inflation will actually drive the universe towards a situation where the potential has the same, where the field has pretty much the same value at every point in space. But then when you solve the equations of motion for the potential, what you find is that the inflaton behaves as if it's a ball rolling down a hill. So if the inflaton field has a particular value, it will try and change its value in a way that lowers its potential energy. And when it does that, it will gain kinetic energy. So exactly the same math as the ball rolling down a hill. So dark energy, there is a potential for it to do that. But if we wanted to form dark matter at very low energies, then it would have to interact somehow with the standard model of particle physics, because most of the stuff in the universe at low energies is made out of standard model particles, out of atoms essentially. And we know that whatever dark matter is, it's very shy about interacting with atoms. So somehow you would have to smuggle that interaction between the dark matter and the rest of the universe in order to create it. Somehow you would have to smuggle that into the standard model in a way that meant that it also wasn't easily detectable in particle detectors. So it's, I mean, there's no rule that says it has to happen, but it's certainly conceptually easier to have gotten your dark matter in place before the universe cools to the point where it's governed by physics that we think we understand pretty well. Does that make sense? Dark energy, we don't know where it comes from, but dark energy somehow lives at every point in space, so we may not necessarily have to create it as such. It seems to be something that's cooked into deep physics. Can I get back to the questions on defects and stuff? I'll come back to those later. I just wanted to maybe let me say what we're doing with the stuff we've got. And let me get rid of this. Hang on a minute. I'm having trouble getting rid of my mouse vanishes every time I share my screen. Here we go. So the issue of post-inflationary perturbations without resonance is that the universe is going to just keep sloshing around the bottom of that hill. The amplitude of the sloshing goes down as the universe expands. The amplitude, there's a friction term in the inflaton equations of motion, which I didn't mention, that's associated with the expansion of the universe. But the universe you can show pretty quickly for a quadratic minimum. Any minimum is going to be quadratic if you look at it, in a small enough region. It's going to behave like a universe that is what we call matter dominated. It scales, its density scales like 1 over the volume of the universe. But it turns out that no one had looked in detail at how perturbations will grow in that universe until about 2010. And then, as it happens, with a colleague or postdoc of mine who was at the time working with me at Yale, Raphael Flauger, and James Gilmore, a PhD student there, who's actually Australian and is living now back in Australia, working in, I think, weather climate modeling, I think, the last time I heard from him. So some of you may have encountered him, but was a PhD student in the theory group at Yale when I worked there. And also Judamzik and Martin, two European researchers. Both of us around about the same time produced papers showing that if you left this condensate to its own devices, eventually it's going to grow gravitational perturbations and it will be fragmented gravitationally by gravitational interactions in the early universe. It won't turn into other particles, but it means that the very smooth early universe will become lumpy on small scales. So these oscillations produce a matter-dominated universe. We know that if there's an overdense region in a matter-dominated universe, that's how we explain the formation of galaxies, galaxy clusters in the universe today. Once the universe becomes matter-dominated, slightly denser regions can pull more material into them. They grow by their own mutual gravitational attraction. Eventually, they collapse. So we showed that these condensates would collapse gravitationally on timescales that were much smaller than that total amount of time that we've only got a trillionth per second. But the universe, because the universe grows by a factor of 10 to the 15, and because overdensities you can show will grow linearly as the universe expands, we can take a small overdensity We can grow it by a factor of 10 to the 15. We have an estimate for how big the overdensities should be, about 10 to the minus 5, 10 to the minus 6 that we get from looking at the microwave background and extrapolating to small scales. So we can make the universe inhomogeneous and collapsed just by purely gravitational mechanisms long before this phase has to come to an end. So what that tells us is that even if we don't produce inhomogeneity through some resonant process, it's going to happen anyway just because of gravity long before this phase comes to an end. And that makes the universe much more interesting because the lumpy universe can do all sorts of interesting things that a perfectly smooth universe cannot. So without, I already said this. So what happens, we could take the equations for the scalar field, which is what's called the Klein-Gordon equation, coupled to the Einstein equations because we're solving them in an expanding universe. But that non-linear matter, like lumpy matter, doesn't necessarily mean that we need full Einstein gravity. We can describe, the Milky Way galaxy perfectly well with Newtonian gravity, and Einstein gravity is, is hard and complex, whereas Newtonian gravity is relatively simple. The problem is, if we want to simulate this numerically, we have two clocks. One of which is the time it takes for the universe to expand, but to double in size, which is what we call the Hubble time. And the other one is the time of that sloshing, which is essentially fixed by the steepness of the potential. And that sloshing time is much, much smaller than the time it takes for the universe to double in size, even during this primordial dark age. And so to make sense of what's going on, if we want to solve that numerically and we want to resolve everything, it takes forever because we've got to watch the field go backwards and forwards many, many times in order to fully understand its dynamics. So what we have, it turns out, is self-gravitating, non-relativistic in the sense that all of the quanta have energies, the total energy is much smaller than the rest mass of the particle, but quantum matter. And so we can take this, and this is like the one slide of equations that I've got. So the action that I've written down here is the Klein-Gordon equation coupled to in an expanding universe. So space-time metric is G, it's determined as minus G. And so we vary this, we put in local gravity, and what we do is we get an equation that looks like this, where phi is the Newtonian gravitational potential. And this is a problem that you can solve numerically if you want, analytically in some special cases, but we don't want to do. So what we do is we assume that the field is changing slowly relative to its mass, which is a reasonable thing to do. We assume that the rate of change of the Newtonian gravitational potential is relatively small. We assume that the gradient of phi is much, much smaller than its mass. So a bunch of things we have to do. And then we say, well, let's assume that phi is equal to this combination of this complex quantity plus its complex conjugate. And we put all of that into the Klein-Gordon equation. We throw away the terms that we've assumed are small, and what we get is the Schrödinger equation. Except the potential of the Schrödinger equation is not some external potential. This isn't like the particle in a box problem, or simple harmonic oscillator problem you solve in undergraduate quantum mechanics. The potential that the Schrödinger equation feels in this case is the Newtonian gravitational potential of the stuff that's described by the wave function. So the wave function describes some density of matter. The density of matter has some gravitational field that's associated with it, and that feeds back into the behavior of the wave function. That means that we have to solve the Poisson equation for the gravitational potential at the same time as we solve the Schrödinger equation, and we have to keep track of those two things as they move forward. And so this is a cool situation to be in because it's an interesting set of dynamics. It's also not an easy problem to solve because you've got these two coupled differential equations, but it turns out that is actually a problem that we were already looking at for a separate reason. And so we're looking at energies or times around 10 to the minus 30 seconds after the Big Bang. Energies maybe 10 to the 12 times higher than the LHC after the fragmentation has taken place. That's densities about 10 to the 48 times those that we would reach at the LHC, so much LHC, you're looking at stuff that's, has the density of nuclear matter. So we're 10 to the 48 times denser than a nucleus. And we're doing this through to about 10 to the minus 12 seconds after the Big Bang. And so when we realized that this was the situation that we found ourselves in, the happy coincidence is that for other reasons, my group had already built a Schrodinger Poisson code. And we've done this, so pi ultra light is something that Frank's extended to include point particles and black holes as part of his own PhD project. But it runs on a fixed lattice. In other words, as the universe expands, the points between the lattice get further and further apart, which is not ideal for cosmology. We use what we call a spectral solver for the Poisson equation, which is a nice thing you can do. And this is work that was done with a master student, Faber Edwards, Emily Kendall, who's now a postdoc with me, and Sean Hotchkiss, who's was working with me as a postdoc, is now a science communicator. And we'd set this up to use for ultralight dark matter, a particular brand of dark matter where the wavelength of the dark matter, quantum wavelength, well, mass is very small, so the wavelength is very large, so you can see, quantum phenomena on astrophysical scales. So I'm not going to talk about that today. That's something completely different. But what it meant was we had a code that if we added expansion, so we allowed for the universe to expand, we put in some sensible initial conditions that look like cosmology and not a galaxy, and we changed the units, from galaxy densities to cosmology densities. We had something that described the collapse of the inflaton condensate in the early universe. An interesting thing is the math that describes this situation was fully visible in the early 1980s, but no one had actually worked out the details until 2019, when this was published. And because of that, we were able to get, and because we made a pretty picture, we were able to get ourselves on the cover of Physical Review letters with it. So as I said, the lattice here didn't grow with the expanding universe, so that meant that we had to stop it. Once things started to collapse, but we could see the first overdensities grow. So what this gets us to, and I'm just going to take a couple of minutes to round out what we're working on at the moment in this particular area, is it tells us that the condensate obeys exactly the same equations as a particular kind of dark matter in the present epoch. So generic cold dark matter on large scales and ultralight or quantum dark matter on small scales. So this means that in the early universe, you can take the stuff that the inflaton was driven by, and you can form an analog of galaxies, of galaxy clusters, and the cosmic web, except it all forms in the first trillionth of a second after the Big Bang. And we know that somehow or other, in order to produce a viable cosmology, it has to dissolve into radiation so that we can get the universe that we see, that we can set the stage for the hot Big Bang. So we can reuse a whole bunch of analytical tools that were developed to study galaxies, like the Pressure formalism, for instance. We can use those tools to understand the statistical properties of the lumps that we form in the early universe. And so just a reminder, cosmic web, we look at galaxies in the sky. It turns out they're not just kind of scattered at random. They form this complex web structure. We can see one of the successes of dark matter is it predicts the formation of this web structure on the basis of very, very generic assumptions about the properties of the dark matter, and we can see it coming up and coming out of simulations as well. So this is kind of a theorist's playground. Any structures that we produce have to be evanescent, but it tells us what is the existence of if we want to make dark matter in this space. And it turns out that the universe is full of very, very locally dense collapse structures, then whatever the physics of dark matter production is happening in a universe that has some complexity to it that we hadn't previously suspected. As I said, the basic model may be 40 years old, but this area has never been explored in detail. It's generic in a wide class of inflationary models. We need numerical tools to do that because we're dealing with nonlinear dynamics. We're building them as we go along. So where we've been since then is we took standard galaxy evolution codes in a regime where we don't have to worry about the small scale quantum properties, and we ported those back into the early universe. And so we can push a long way into this nonlinear regime. And so when we saw structures that had a mass of maybe 20 kgs, But we're also about 10 to the minus 20 meters across. So remember the proton has a mass of about a size of about 10 to the minus 15 meters. So this is 10 to the 15 times smaller in volume than the proton, but also a mass that's kgs rather than 10 to the minus 27 kgs. So this is a simulation. So this is e to the 14 time, the universe has grown by a factor of e to the 14, so 10 to the 4 maybe after, and 10 to the 5 after inflation has ended. And this is a slice showing the through our simulation showing the density of the universe in a region of space that's would fit inside of an atom. As the universe evolves, that structure sharpens up, and you can see this kind of web-like structure with little blobs of inflaton being held together by their own self-gravity on scales of about 10 to the minus 20. Here's the smallest one we found, and here's a picture. Well, it's a silly picture of it, but this thing is this tiny, as I said, 10 to the minus 20 meters across, weighs about as much as a spaniel. Similarly, we can find the analogs of galactic halos made out of inflation of the inflaton particle. We can compare that to projector results and see that everything agrees well. We've zoomed in further. We've gone in to the point where we can see the collapsed regions at the center of these inflaton regions, and we can see things with a distinctly quantum mechanical properties. And again, we can show that if collapse goes on long enough, if we use most of that 10 to the minus 12 seconds, most of that 10 to the 15 growth, in a matter-dominated or currently matter-dominated phase, those will collapse to the point where they'll fall inside of their own Schwarzschild radius and form primordial black holes, and then they'll decay very quickly, by the Hawking process into all kinds of particles. Likewise, we're moving a lot of stuff around. We're moving it very quickly in the early universe. So gravitational waves are sourced by moving mass, and the most recent result that we've got in this area just earlier this year was a result in PhysRevD where we showed that we could produce, for very extreme circumstances, we showed that we could produce gravitational waves that were formed that would create a stochastic background of gravitational waves in the present universe. And I'm just about to wind up here, so I think I'm pretty much on time. So far, these are of academic interest. They're way below the sensitivity of LIGO or of the subsequent Einstein telescope and amplitude, not dissimilar frequency. And we've also had to make some pretty extreme assumptions about the inflationary era to get this to work out. But we have some other models where this nonlinear phase gets underway much earlier. In those models where we would expect that inflaton, that we would expect the gravitational wave production to be a lot more intense, and that's something that we're looking at the moment. So we've got lots of stuff that we're working on. We haven't talked anything. I haven't talked about resonance, but that's a different way to, once the inflaton fragments, then if it doesn't immediately turn into other particles, what happens next? We talked just a little bit about primordial black hole formation. They've never been seen in nature, and if you do see one, you get a free trip to Stockholm. But if theories predict primordial black holes that that would still exist today, and we don't see them, that's still a win, because we can then rule out the theory on the basis of that prediction. We're interested in gravitational wave production and stochastic backgrounds that might be detectable in next generation detectors. We'd love to be able to describe thermalization in this system. How does the process of thermalization complete? How do we take all of the energy out of the inflaton field? And if we have any left over, would that, for instance, constitute dark matter in the present universe? And so our goal is to build a self-consistent simulation of the early universe from the inflationary phase through to the end of the primordial dark age and beyond, in order to better understand the predictions of inflation for cosmology as a whole. And on that point, I'm going to finish. So now, next batch of questions, please.
Thank you, Richard. That was so much information. It covers pretty much all the field.
Hopefully not too much information.
Yes, and as I said before, and I can see the participants number has doubled since your talk, so that's awesome.
That's
I'm
always
sure
really
that
bad when students leave halfway through the lecture. Any questions? We've got a bit of time. I don't know when the next thing starts, but I'm happy to stick around. And I've already burned some of my question time, but we got any others?
Yep. Yeah, we got a few minutes before the next speaker, and please fire away if you have questions. You can also put in the chat.
Yeah, I'll go back to. Close my. Cool. And there was a question about cosmological defects. So cosmological defects are situations where you have the obvious easiest one is a U1, as like the kind of field that is associated with electromagnetism and has some phase that's associated with it. And so if you set up a situation where, you know, as you go around a circle, the phase changes, and then you make that, you know, very long and extended, what you have is something that corresponds to a string. So it's not a particle state, but it's a state of a quantum field that would behave like a it's long and skinny. And the reason it behaves like a string is you can't continuously deform the field to get rid of that winding. Similarly, you can make what are called domain walls. Those are different from superstrings. You know, they're not related to string theory strings, but these are large objects that would exist in the universe. And the theory goes that if you create them in the early universe, you know, then they're stretched by the expansion of the universe. We can, if those things form before inflation, then, and because inflation expands the universe dramatically, it decreases their number density, so it would effectively erase them from the present universe. If they form after inflation, then they can't form in sufficient numbers or have sufficient densities to disrupt, you know, the rest of cosmological expansion. So there is a possibility that for instance, you know, a network of cosmic strings exists in space, and we look for them, for instance, you know, by the impact that, you know, if you have a long, massive line essentially, and you put that against a CMB, then you get, you know, lensing patterns that will, you know, be different from the kind of point source lensing patterns that you get from galaxies. So there are ways of going and looking for these things, and ways of putting bounds on the total energy density from, say, a network of cosmic strings. But you know, whenever we go and look for them, we obviously don't find any. So we can, you know, we can squeeze down the contribution they make to the universe, even though we can't rule their existence out in full. But whatever, you know, whenever they form, again, it would have to be, you know, if we look at the kind of raw materials we have in the standard model of particle physics, we don't seem to have, you know, ways to produce persistent cosmic strings in particle physics. So in particle physics we currently know, so presumably if they did form, they'd be forming out of, you know, particle physics that lies outside of the standard model, and presumably, but not necessarily, at, you know, at LHC energies and above.
Awesome.
Cool. Well, thank you very much, Ben.